this is going to be pertinent to the little quick lab you guys are going to do in, 20 minutes or so. So really what I wanted you to know is a lot of this is going to be background for this unit. So what are some things you guys read about? I'm just going to go around the room, okay? Some things you read about in your solubility reading. Maybe even some things that you're like, hey, I do know what this is, or hey, I have no idea what this is. So Chloe, what's something that you read that you, ooh, this doesn't come off the board. Oh God. Expo Neon is not a no-go. Okay, Chloe, your turn. Tell me what's on the board. What you read? Yeah, we won't do this again. Okay. Live and you learn, guys. Ready when you are, Chloe.
That the hydrophilic is loving, and I have like the L underlying, so like loving is like forward.
Yeah, and you guys know like what the word like philanthropist is? What's a philanthropist? Okay, so they donate because they're sharing their love for some sort of charity, and they're donating money to it most of the time. So I feel like usually means love, okay? And then hydrophobic means like phobia, okay? So you don't like that thing, so you don't interact with it. Alvin, something else.
I got reminded what molality was.
What's the symbol for molality?
Lowercase m.
Lowercase m. How is that different than molarity?
It's moles of solute over kilograms of solution.
Moles of solute
Solvent.
over kilograms of what? Solvent versus molarity, which is
Moles over liters.
moles of solute over liters of what? Solution. Yes, so we will talk about the differences there. Molarity we use all the time. Molality we only usually use in special situations with colligative properties, and on occasionally also we convert from something molarity to something molality. I'll come back to this table. Courtney.
There's like 3 delta H's, and delta H is solution.
Delta H is solution is equal to delta H 1 plus 2 plus 3. We're going to talk about that today. Somebody else at your table?
Miscible liquids and immiscible liquids. Miscible liquids are two liquids that mix together. When they're together, and immiscible is the exact opposite. When they don't mix.
So miscible means mix.
Miscible?
It's miscible, S-M-I-S-C, got miscible. And immiscible means not mixing. Good. AJ's table. Okay, so like amount of solute could be particles that are present. So who has more particles? Sodium chloride or aluminum chloride? Why aluminum? Yeah, aluminum chloride, AlCl3, dissolves into Al3 plus 3 chlorine ions, so there's going to be 4 particles there. What's the I called? Van't Hoff factor, right? So the I is the number of particles that are present, so there's 4 particles, the I factor is 4. Sodium chloride only has 2 because it breaks into 2. So that's going to be related to colligative properties probably later this week. Levi's table?
Volley are between solutions and systems.
Right, they're this weird intermediate particle size that don't act 100% like solutions, but don't really act like solids or liquids in that sense. So they have special properties like Tyndall effect. And who's ever driven in fog? Okay, who's ever seen fog? Okay, most of us. So fog is a solution. It's weird, not all solutions are aqueous based. So many times we'll just go, oh, aqueous solution, and you just understand it means mixed with what? With water. But if I just say solution, most of the time you guys probably just assume I'm talking about water, right? But there's all kinds of solutions. You have gas solutions, liquid solutions, solid solutions. It's an interesting mix. So fog is a liquid gas kind of solution, and so it actually acts as a colloid. Kirk's table, one more. I just skipped you guys. Come back. Facts. Okay, so what's a real world example of that? Of decreasing solubility of a gas and increasing temperatures? Anybody? Decreasing solubility of a gas in a liquid solution at higher temperatures. Okay. It's not real world for me. None of factors all the time. Yeah. Soda. More. Elaborate.
Like the carbon dioxide starts leaving the soda as it gets cold.
As it gets warmer, so it goes flat. Right. That's just a flat soda versus a cold soda, which is nice and bubbly. Something else I skipped, Jack. Somebody over here. You over here.
Yeah. When you're calculating boiling point elevation or freezing point depression, there's a constant for water, K, B, F.
KF and K BP.
BP, yeah.
Okay.
One is, for freezing, it's 1.86
Degrees C per mole.
degrees C per mole, yeah. And then the other one is 0.51 degrees C per mole.
Yeah, Malal. It's not like a jungle cat. Okay, it's Malal. It's like a how you say it, little whenever you're saying it. Okay, so overall, who feels like they remember a lot of that stuff from honors chem? Maybe some just common factoids that you kind of come into counter in your first 16 years of life. Yeah. Okay. For me, okay. So some of these other factors are going to be related to the polarity of substance or not. And sometimes we have these huge molecules, and the huge molecules can have like 3 or 4 different functional groups on them. So if you have a couple of, let's say, 30 carbons, and they're all arranged in like the different rings, and you have mostly all carbon to hydrogen, carbon to carbon, carbon to hydrogen, maybe like 1 carbon to sulfur bond, occasionally sporadically on there, that entire molecule would most likely be hydrophobic, which would it interact with water, yay or nay? Nay. So is it polar or nonpolar? Nonpolar. So it'll dissolve really well in what? Oil and fats and benzene and other nonpolar solvents, but it will not dissolve very well in water. Okay? Why would that be important in the human body? We take a lot of food and particles in, right? We take a lot of organic substances in. We are organic beings. A lot of the food we eat, of course, is carbon, cho, chon, chompy. You guys know what I'm talking about? Biology, carbs, lipids, proteins, and nucleic acids. And we take in vitamins and all kinds of things. Have you guys heard of fat-soluble vitamins and water-soluble vitamins? Okay, so there's some things that you want to be fat-soluble so that the vitamins kind of come into contact with your phospholipid bilayers, and they'll penetrate the cells and get moved to where they need to. And then you have some things that can just get washed out in your pee. You just pee them out. Okay, so if you take who takes a multivitamin? Anybody? Flintstone. I used to take those for a long time, and I changed to gummies. So I'm a real adult. So sometimes we want those things to be, so they can be almost toxic in high dosages. So we need them to be water soluble to come out in our waste. Sometimes we need them to stay for a longer period, so they might be fat soluble. All right. So these groups up here, what would you call this group? Functional group. Alcohol group. This one. What's it look like? It does look like CHO, but give me what it looks like in a functional group. C, double bond O, H. So, anybody know the name of this little functional group? Say again? Aldehyde. Think like high, like on the end. This is on the end of a molecule. Like, who's ever been beaten on the hide? Like, gotten a whooping. Okay. Hello, Sean. How was Chicago? Chicago. Okay, you can tell us more later. Sit down right here and Lucas will see. Okay, so this is an aldehyde. CO in the middle of a compound is C double bond O in the middle of a compound. It's like da da da, C double O, da da da. Ketone. It's like a key in the middle of like you want to stick the key in the middle of the door. I don't know. Okay, ketone. And then CO, so it's our double bond O, OH. Say again. Come on, Arushi. Carboxylic acid. Why is that a carboxylic acid? It's because it's like C double bond O, OH, blah, 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 blah. So why is this considered an acid? Because not just because it has an H on it. Not only because like most things have an H on it. Because it has an H on it, that's like peace out. Makes an H plus. It donates an H, right? Did you just say skirt? Okay, so this is going to be like what's left over. So what commonly has the kind of the functional group on the end with COO negative? That's a polyatomic ion we use really frequently.
Carbon.
Say again? Acetate. C2H. Oh, let's not do it that way. Let's do it this way. CH3C double bond O. Yeah. So there's acetate right there. And that acetate makes acetic acid, which is what the H is attached to it for. Okay. All right. So the most of that information is kind of review, but we're pulling it together in like just a little bit of a different way. Okay. So let's scooch from this for a second. Let's do IMF talks. And I did not have to do Scantron, so unfortunately, I have to be the bearer of bad news. I have to say off like 30,000 letters. You ready? And I want to do this so that you can get off of IMS for a little while after today. I'll take questions at the end. You need something colorful to check with. So if you don't have something colorful, raise your hand. AJ. I hope that you actually honestly did this so that this is not just a waste of my class time for me to give you just a bunch of letters that mean nothing. Anybody else? Orange? Anybody need orange? It doesn't work? Oh, okay. I was like, assume you're with me. All right, so I'll take questions at the end. 1A, 2A, 3, D, 4E, 5D, 6D, 7A, 8B, 9C, 10A, 11B, 12E, 13B, 14E, 15C, 16B, 17E, 18A, 19B, 20A. You guys good? Okay, I'm trying to go too fast. 21B, 22A, 23D, 24B, 25C, 26A, 27A, 28B, 29A, 30C, 31E, 32B, 33C, 34E, 35B, 36B, 37D, 38B, 39E, 40A, 41A, 42A. Say one more time. 42A. 40, 41, 42A. 43, E. 44, C. 45, D. 46, E. 47 through 50, D. So 47 through 50 is D. Okay, and then 51, B. 52, C. 53, D. 54A. 55E. 56A. 57A. 58A. 59C. 60 A. 61B. 62A. 63D. I'm sorry, lies. B. That's a B. 63D. 64D. 65E. 66E. Any that you guys need to review them? Count how many are right out of 66 at the top of your paper. This is more for me to see where your mastery is right now. Please give me an honest response, because if you just say I got 66 and 66, it does not help me at all with instruction. Anybody, any that I need to repeat right now? Is that a no? Let me give you guys a chance to actually review these before I start going over these. You say 52, so 52 is C. So I think I'm gonna wait till the end of class after everybody has a chance to actually peruse their old responses before I start going over individuals. But on the top of your paper you have how many out of 66, correct? So you got over 50 out of 66. Anyway, I just want to know. All right, 46 out of 66. All right, what's 46 out of 66 except for some of it? Yeah, it's like a 69.67. Okay. All right, so that's a 70%. So, okay, I don't want to know any more. All right, so scooch that to the side, so I'm going to look over those before I move on to our lab situation. So, before I do that, you guys have your unit review from Friday, condensed states unit review. And so, my goal is to only review 3, 4, 7, and 8. If there are any others, let me know. 3, 4, 7, and 8. We're kind of just like tying up some loose ends here from our stuff from last week. All right, so question number 3 said, in each pair, I'm just going to ask one of you guys to help me out, okay? So, in each pair, which substance would you expect to have a higher boiling point? And then tell me why. Alvin, A.
Xenon,
Why?
figure it out.
Use your words. Give me more.
That's all I wrote.
Somebody help him.
It has more mass, so there's more electrons, so there's a greater attraction. So it's good to have more.
What's the word that means electrons shift around? Polarizability. Thank you. Write the word polarizability because that is the term to use that really explains it. It just, it's impressive to use the right term, just to be honest, on an AP exam. So if you're walking around the world to say something, you can say it in one word, it's easier. More polarizable because it has more electrons because it's heavier mass. 3B, Courtney.
CS2,
Why?
because it's more polarizable because of the greater mass.
Right, so the ligands of O versus sulfur, there's more electrons, going to be more polarizable. Higher London surge forces. C, Levi? Okay, so I put both are equally nonpolar as well, so they're both nonpolar molecules. So then you kind of have to go with a secondary thought. All right, so they're both nonpolar. You could look for polarizability, right? Chlorine's got more electrons. Chlorine, diatomic chlorine's got, 70 grams per mole, so it's going to have more electrons as well. Some things its got numbers 30 something, or no, 70. So it's got 34 electrons to work with around versus carbon plus 4 hydrogens only got 16 electrons to work with. So you can go with polarizability. However, you could argue that methane CH4 is more complex, so it actually has more surface-to-surface contact than chlorine might. So I would be good with both as long as you explained it and not just said could. All right. D, Dinky. Why? Ionic versus covalent all day. E, I'm sorry, this should be that. AJ, E. Okay, so phosphorus trihydride could undergo dipole versus amino bonding. So 3, 4, so on 4 now, phosphide crystal. Kurt, A, hard brittle crystal, electrically non-conductive, aqueous molten state, or in aqueous molten conductive. Ionic, good. E, soft solid with low melting point, blah, 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 Riley. There was something that did not suggest that. It says all states of the substance are non-conductive. All states are non-conductive. In our network covalent, which was conductive. One of the carbon types. Who's writing with it right now? Graphite. Graphite is conductive. So that's our one exception in network covalent. That means not conductive, but graphite is. So that definitely should not be network covalent. Can somebody do something else, Sean? Molecular solid would be polar, non-polar. It's hard to tell. It would probably be non-polar because it doesn't. Polar sometimes can be slightly conductive whenever it's split into two parts. It's ion dipole. So for C, hard solid, high melting point, Jack. Network all the way, and it's non-conductive. So this one's weird. So a very hard solid with high melting point, non-conductive solid or molten state.
Graphite, like the one.
Graphite is the one exception. I wish I'd been more specific there, so I can see why B and C would be confused. But C is definitely more network, and I just put on my paper exception graphite. Okay, 7 and 8. 7, we have. Oh, this is our paper question one. It's Eslan, did I spell it wrong? Did I say Eslan? Or
No, it's
Spillane. Spillane. Oh, I put Spaniards, okay. It's Spillane on mine. So butanol versus diethyl ether, who's higher vapor pressure, anybody? Rom-com? Why?
Because it has a weaker level, it's not good force.
Of what?
It only has LDS what butanol has.
Not quite. I was good with you, and then I'm backing up. Jacob?
I was thinking the same thing as here. It has the large dipole on the end right there, the orange part.
You're talking about butanol, right?
Yeah.
Butanol doesn't have dipole necessarily, not as its most significant force.
I mean,
What is its most significant force?
H.
Hydrogen bonding, okay, and that's what Kirk said, but there's one thing I didn't like what you said. Diethyl ether looks like this. Come on, Kirk. IMS.
Dipole?
You got this little lone pair on the oxygen, so this one's gonna be like, it's like a bat. Okay, it's gonna have like a partial negative region, so this one's gonna have a polar section to it, so it's gonna be able to dipole on that section, but London dispersion force on everywhere else. And so the cumulative nature of those London dispersions with that dipole is lesser than, was it butanol? Butanol, 1, 2, 3, 4. So this section here can do what? Hydrogen bonding plus the London dispersion forces of this branch section, but still the singularity difference in the dipole versus hydrogen bonding. So it's simply because of the lesser attractive forces, but not because it's just London dispersion. 8 is the other one, yeah. So below is a cooling curve for 1 mole of the substance. Which parts of the graph is representing average kinetic energy of the molecules, is showing average kinetic energy of the molecules changing. Avery. 1, 3, and 5, good. And that's the slanted sections, so the diagonal areas. Which section represents heat removed related, is primarily due to lowering of potential energy of the molecules, Levi? 2 and 4, so the other sections, right, that's where potential energy changes. Which portion corresponds to a release of the heat of vaporization, Emma?
1.
So what's heat of vaporization transition between? So where's liquid and gas? On our heat curve.
Oh, it's 2.
Yeah. So remember, I did a heat curve for you guys, and I said cool curves are just opposite. So 1, 2, 3, 4, 5. What is 1 representing? Gas cooling down, and then here's representing transition from gas to liquid in physical equilibrium. And that's heat of vaporization is one way to say it, but it's actually the opposite of that. So heat of condensation. It is still the same number. The number is the exact same. It's just one's positive and one's negative due to the release of heat or the gain of heat. And so we would actually talk about it being negative because it's releasing energy. 3 is straight up liquid. 4, liquid to solid, and that's called delta H of, say again? Freezing, thank you. And then 5 is our solid. Okay, and then 4, did we do 4? I mean, did we do D? Indicate the melting point of the substance, Allie. We're out on 4. At the, so tell me, heart or star?
What did you say? Hard star?
Here's my heart right here.
No, hard.
Yes.
Sorry.
So it's exactly when the liquid begins to transition into solid. So at the beginning of 4, not the end of 4, will be our melting point technically. But it is the same temperature because our temperature is on this axis over here. So the temperature is the same, but I just want to see if you guys knew where it would start. 5 or E, indicate how supercooling of the liquid affect the graph. Look at your textbook. Yeah.
Whenever you're on the part of the line that's at 3, it kind of like dips below 4 and then goes back up to it.
Okay, so here, 1, 2, 3. So it's going to go like this, and then come back up. Okay, so what's happening there? It is supercooling, but can you explain that? It's super cool, guys. Come on.
So,
Okay, so whatever this liquid is, probably has some sort of structural arrangement as a solid that makes it really tightly packed. So it's cooling, it's lowering its kinetic energy, they're slowing down, but they haven't really arranged themselves in their solid structure yet. So they're slowing down so much, you've super cooled them probably really slow. And then you jostle it, and then they pretty much crystallize in an instant because they've arranged themselves immediately into their crystalline form. So then it immediately freezes, and then of course it would freeze all the way. So it's almost like the super saturated solutions where you put a crystal in and it desaturates. Okay, you guys feel good? Okay, good about that old stuff, ish. Yeah. Part 5. Which liquid is expected to have a larger surface tension at the given temperature? How will the substance form a convex or concave? Okay, so this one has actually some old information in it too. So we have carbon tetrachloride and water, right? Carbon tetrachloride, overall polar, nonpolar. Nonpolar, water. Okay. So what IMF is this experience? And then this one, hydrogen bonding. So London dispersion versus hydrogen bonding. All right, and then it says, it's in a glass container? In a glass cylinder. Okay, so what's convex look like? Think about like your meniscus in a graduated cylinder. What's this? What is this? Okay. Concave is like a cave in. Like a cave goes into a mountain. Convex is supposed to be like kind of a bridge. Concave, cave, and then I didn't mean to draw this underneath here, but I just knew that you knew from here what's happening on the glass. Like, why is it pulling up? There's a word for it. I'm good with adhesion. Okay, adhesion, but why? Okay. Okay, but why? Like adhesion and capillary action. Capillary action is just like the overall change going up a capillary, but it's caused by adhesion and cohesion. But why can this, whatever this substance is, why can it do that? Anybody? You guys have probably you told me this before. Like you'll try to pour something or take a pipette, try to pull something out, put another one. You're like, it's dripping. Usually alcohols and other non-polar substances will do that. But water does a really good job of clinging to the side. So what do you think the water is doing with the glass? Any takers? Say again? There's only one attraction water will really have a strong force with. Hydrogen bonding. Good job, guys. Okay. So this is probably hydrogen bonding, and it's causing it to become attracted to glass because of its polarity. And glass actually has some sort of silicates in it and some other impurities. And so the ions that actually kind of are inherently in glass, we're a silicate for that example, pull the water up. Whereas carbon tetrachloride, it probably will be convex because it doesn't really attract to the glass, but more so it will attract to itself, CCl4, CCl4. So it'll attract to itself within here through cohesion, because remember co means like cooperate together, so it'll really stick to itself, but it won't stick to the glass as much, so it doesn't create that meniscus. It has like a convex appearance actually instead. Good question. Another one on you guys? Right now? Yeah.
Can you go to number 9? It's the one.
Molar heat of vaporization, how many kilojoules heat will be required to vaporize? Okay. So, was it 125?
125 milliliters.
Okay, so 125 milliliters of water. And it says delta H of vaporization is positive 43.9 kilojoules per mole. How many kilojoules would it take to melt or to vaporize? So you guys tell me your starting point. I have to start with 125 milliliters. I can't do squat because that's in moles. What do I do first? Convert to grams. So what's my conversion? 1 milliliter to 1 gram of water, and then to 1802 grams of water, and that's 1 mole of water. And then 43.9 kilojoules per 1 mole, and then estimate.
4.4.
4.6.
You guys are great at estimating. 3 or what? Give me 3 sig figs. 3 or 5 kilojoules. Okay. So it'll take 300 kilojoules to vaporize 125 mils of water. Okay. I want your packets. Pop them over here. I want to see those. And then grab, yeah, let's do this. I might have to have you guys read this for a couple minutes while I finish grabbing the alcohols. It should all work out just fine. I've only done this lab once. Put your packets over here with your unit or in the multiple place. And then grab this sheet, begin reading it, and then I'll do it to you. You might want to highlight something on the. You might want to highlight
Yeah.
Yeah, I had Duke
I have so many notebooks out here. Here, instead.
Everyone's back.
Thank you guys for reading and highlighting. If you want to highlight it, it's probably one of my best subjects. If you want to add information to your lab notebook, that's fine. Here's the other. Alright, so you're not drinking the samples today. We have grape Kool-Aid, okay, you're not drinking this. And this right now is 28% isopropyl alcohol. 28%. So you are changing two things for me, where it says procedural questions later at step 4, draw 2 milliliters of percentage isopropyl alcohol. You see that? Procedure step 4, the very lower left corner. Yes. Mine, I have a short version. Let me actually go to your version. Your version. Okay, let me tell you this now. Alright, so before the procedure begins, where it says just procedure, do you see that? Okay, you need to actually, kind of see what I'm doing for the Alright, so you can see over there? Yeah? Alright, so basically you're gonna get this little syringe, I've got them, they're new syringes over here. And you're going to attach this little, it's called a column chromatography tube. So it's a column of really, really tightly packed silicates and some other things that can attract small particles. And so it's based on attraction, which is why the pre-lab information gave you those big, huge pictures, and pictures you're supposed to see, portions that are polar, portions that are non-polar, and so forth. So this little tube, which is here, sticks onto the end of the syringe, and on the end that's inside, you can get it simply in there. These are like $20 a piece, so we can reuse them over and over again. So if it's a little discolored, it's fine. These are actually all new here. So then you're going to get a little beaker of isopropyl alcohol. So we have to dilute it first, though. The isopropyl alcohol, you're going to pull it up through the syringe, and it's going to hydrate your sample, hydrate your chromatography column. So just next to procedure, before anything begins, just put hydrate column. Okay, hydrate column, that's what the isopropyl alcohol is. This is most supposed to be marketing free. I'm giving you this as we go. Alright, so it's going to just say, fill a couple milliliters into the, after you hydrate your column, you don't want the alcohol in there anymore. Push it onto a waste beaker or some sort of waste area. You don't need it anymore, you just need to be hydrated. Then you're going to get some of the grape Kool-Aid. You're going to have a little beaker of it, and this is where the actual procedure starts. Placing it into a beaker, can you grape soda or grape Kool-Aid, fill a couple milliliters, what do you see? And then attach the mini column to the syringe. You can see the first. Right, you're going to take this on and off like 6 times. Sorry, this step's not in here. So, what is my very, very, very first thing? Column on, hydrate it. Push it back through to get rid of the alcohol. Column off. Then next step. What does it say to do? Place the syringe into the grape drink. Pull it up. Okay? Then the column goes back on because the juice can't go through it and back. So basically a one-way shot. Okay, so I just want to make sure the first steps are clear. After that, your soda or your grape juice is in here, and then you're going to push it through, which is the next. After you touch the mini column, push on firmly, point the syringe away from you, push the plunger until the soda is being forced out of the syringe. What do you observe? Okay, so this is still on here. Now I'm going to give you guys little well plates. I want you to see the colors as they go. So when you're dispensing your fluid after your soda's in there, dispense it into like a well plate and fill the well plate up. And you'll probably go through 2 well plates with the amount that you're pushing through this today. Okay, so the final here, 1 syringe, 1 column, and then 2 well plates. Alright, so after you've pushed word it out, detach the columns from the syringe. Okay, draw in 2 milliliters of the solvent into the syringe. 5% alcohol. Write this down, this is not on there. probably one of your group members taking this 28% down to 5%. How are you gonna do that? Math. Okay, I'll check your math before you do that. Okay. So detach the pump from the syringe, draw 2 milliliters of the 5% alcohol, reattach the syringe, slowly push the solvent through the syringe, observe the colors of the fall. So it's your well plate. Okay? Blah, blah, blah. Blah, blah, blah. And then, yeah, well, you'll just keep sequentially going with it. You're important. So yeah, so keep going. And then this time, I should give you, I have like 3 versions of it. I should give you the one of it. Alright, so after you do your 5% alcohol, put your kind of intermediate step that's not listed here. 25% extra alcohol. So what you do with 5% alcohol, top the syringe, the column off, pull up 25% alcohol. That's not on there, so I would look at 25%. Do the same thing, push it all the way through. So just say repeat with 25%. Okay? Just after you did your 5%. It's going to be before does this prove your hypothesis. If all the color comes out together, the solvent's too strong, just need to put a non-polar. Non-polar, make the solvent less non-polar, adding more water, suggest blah blah. That part we may not get to. So after you've basically done right through 5% alcohol through, 25% alcohol through, stop and let's assess the situation. Does that make sense? When are you popping this off? After each elution, and then before you pull more information or more solvent in. Okay? So you probably need to maybe have somebody go ahead and do the math for that. I'm gonna leave this set here. 1 syringe, 1 column, 2 well plates. Yo.
Are we looking at our table first?
I said a group, sorry, I have enough out there for 6 groups, so groups of 3. Yeah, this is too little of effort to do 5 people in a group. Groups of 3 or groups of 2, but groups of 4 are useless. I don't really get to do anything. So, how much do you guys think? Maybe make 10 milliliters. 10 milliliters or so with 5% alcohol and then the 25% alcohol. Looking up. I just give a lot of oral instructions. We need help. Yeah. The original alcohol is 28%. Do not get into like check your math. Same thing, molarity, just the percent there instead. So what are you doing? Okay. Or what volume? Math people, listen up. Raise your hand if you're doing the math. Raise your hand. N1V1 equals N2V2. That's the dilution equation, right? N is molarity, a form of concentration. Is it percent as well? Basically, it's like I have this much stuff in this much container. So do N1V1 equals N2V2. Take your 28% original to 5% diluted. And I said make what volume of your diluted? 10 milliliters, that's V2, plus V1. Thanks. You have confused looks on your faces. I'll figure you out here. Soon enough.
to his eyes, the point of Wait,
I would use
how much volume?
a volumetric type.
Oh yeah, 20.
Volumetric type.
Somebody put a scoop in my speaker. Oh my god. Hold it, there's nothing. Your waist. You got waist right here. Your shirt. Well, what? Your water boy. Put on your goggles. It goes on like this. Yeah, the short end goes on like that. Because that way, that way you can actually use the long end. That is just yeah, it goes. Yes.
Here's the volumetric for one for 10 milliliters. That's not labeled, but I know it's not.
Are there 100 milliliters? 5 milliliters. So I'm going to assume you want 100. Yes. And then just put the rest back in the thing that goes with it. The beautiful waste.
And the little end goes on there. Little end's on first.
So we have to put it right now.
By 28% when you're done, don't waste my 28%. So let's do that. Thank you. Thank you.
Alright, you guys talk switch. You guys need this thing? Okay. Oh, 28%? If V1 is clear. If V2 should be taken. V1 should be.
So don't push too hard through the column, you'll destroy the column, and then I'll have you buy me another one for $10. Push really slowly through the column. I only have a little bit of grape juice, so it's gonna go a long way. You only need like less than 5 milliliters.
There you go. Yeah, here. Well, we still need to point back to yeah. Alright, so yeah. So next to
So, note to self, we're learning as we go. Who started the grape juice already? No one started grape juice. We're gonna put 5 milliliters in, pull after you pop the palm off. Pour 5 milliliters of grape juice into the syringe and then put your palm on and push the button.
select bubble. I pull up, then push it back out. But I gotta pull it up because it's almost a little bit. This feels joke Alright, we got one hydrated thing. Yeah, no, I need grape juice. What grape juice do we need? A bunch? World's best graduated film. Doesn't have any numbers. Is that enough?
Really slowly push yourself into the well plate.
Alright, so the red one is for grape juice. Okay, so okay, I take out this, put this on the shelf. Let's go roll it. Wait, do I keep two? Yeah, take it off, hold it, put it back on. Now it's roll. No, it's like, it's really tight. Thank you. Oh. Yeah, I have no idea. No, no, it doesn't have that much. It doesn't have this much.
Guys, use your full 10 milliliters of your 5% and your full 10 milliliters of your 25%. Where?
Yeah, so it's not purple anymore. It's red. Yeah. What happened? Read the question. Oh, it's this?
Alright guys, I'm hoping you all your results in like 5 minutes. I don't know if that's realistic. Alright, so here's
Reddish. No.
Is that the 20?
Have you guys made the 5% through? Did you already put all of the 5% through? Mine says it's still red.
Well, we already did the 5%. No, but we just did the 5%.
Oh, okay.
Yeah, why are you doing this? Just accuracy measures. No
You.
Yeah, you guys need to get your data.
Not 80%. Oh, you do it better.
So this idea was supposed to be for Martinez, but State, Carolina, and Duke, the red, the light blue, and the dark blue. But none of it's not that hard yet, so no.
That's the ugliest color in the world.
There's so many reds.
Sorry, the Duke lost. Whatever. One of them has fucking one, and one of them's not, so.
So many reds. Why wouldn't it?
All right, guys, clean up. Everything can go down the drain except for my alcohols. The alcohol should go back. Get all the blue. Get all the blue out of the blue.
So we're gonna dump all these. This is stuff. That goes back in the pieces. Yeah.
All right, I have like 10 minutes left with you. Come on. Clean up. Guys, if you're sitting on your butt, clean up. Clean up now. Yeah, just draw the water up and, yeah, put water in a beaker, draw it up and down. You always wash everything out. What are you talking about? Oh, yes. Just making sure. People leave me messes. Messes. Alright, those of you in the front, we're going to talk about this in a second. I will tell you homework, because I'm not going to get to the questions I thought we would today. There's going to be 1 through 7 embedded within this, because they got to guide you, so I don't feel so bad. But I need to guide you, I need to like give you some more information before we can do actually all of these. So, but exercises 1 through 7, most of these answers are displayed correctly, so, okay. Just because we can't get to our problem set just yet. All right, come on, guys. 3, let's go. 2, if you're still cleaning, you're gonna be quiet while I take some time to review some of the class. One. Okay, let me tell you guys at the front what I need, and then I'll ask for the last 5 minutes to be, let's talk about concentrations. So the goal of that was to pull together IMFs and concentration kind of information. So we did a quick talk about percents. We can use percents just as a concentration, just like you can molarity, molality, and some others. So since I'm not going to get you all the question type stuff that I'll get you today, you guys are going to do the sample examples within your NSMI readings 1 through 7. Write that down for yourself. NSMI reading examples, sample exercises 1 through 7. The answers are down here, but I want to see all the work and units and so forth. Now, if you get stuck on something, we will make progress on that a little bit tomorrow and on Wednesday. But we have a short week, so I probably will ask for you to make sure that you give a really healthy start to all these. So like for example, this one, solutions prepared by mixing 1 gram of ethanol with 100 grams of water to a final volume of 101. Calculate the molarity. Let's start this now. Ready? Let's roll. Let me just do a quick screenshot of this and I'll help you guys get started. Now, you guys have your notes of like what's molarity, what's molality, what are the units for blah, what's units for blah, so that's why I'm hitting this now. And I have like 5 minutes, so you know. Say again? This is one exercise 1. Okay, so what? Calculate the molarity. What's molarity? Moles of what in this case? What's the solute? Ethanol. The solute's always a smaller quantity between the two, okay? So moles of ethanol over liters of solution, that's going to give us molarity. Okay, so how do I get moles of ethanol from this given data?
You have grams and formulas.
Okay, so you have 1 gram of ethanol, C2H5OH. What's the molar mass? 46. Somebody do the math for me. 0.02 what? 215? 0.0215. I'm guessing there's some consensus here. Okay. So you see how I'm writing out the quantity that you're referring to? Please do not neglect that, because if you just put moles, I want to talk about water or ethanol or some unknown thing that you've made up. So this is your mole. That's going to go in our numerator. And then what's my liters of solution?
0.1.
Take that divided by 0.1011 liters of solution. Boom. What's my molarity?
215.
Say one more time. 0.215. And that's of ethanol. Okay, so leave all of your work below and then make sure you're squaring off or circling your finals. But if you label it, you've already done half the work for another section of this problem, right? So molarity we just did. Mass percent. What's mass percent? What's the formula? How do you do any percent? Part over total. Okay, so part, sorry, it sounds like someone's clicking here. Part over total. So part that we're looking for is the mass of what? Ethanol. Okay, how many grams of ethanol do I have? Okay, so mass percent is going to be mass of ethanol over what? Grams total. And how do you do any percent? Times 100 at the end. Okay, what's the grams of ethanol? 1.00 and total? 101 total. It's 101. It's not a point. That's a 0. Grams total times 100. What is it? 0.99. Right there. Yeah. Okay. Okay. That's our percent ethanol, which would make sense. It's like less than 1%. It's less than 1% of the total sample in terms of grams. Okay. So that's mass percent. What's mole fraction? You guys did your reading. What's mole fraction? Kind of like the ratio in a fraction sense of the mole. So how many moles of ethanol did I have? So moles of ethanol over total moles. That means we have to go back and do what? Yeah, we got to get moles of water and add it. So how do I get moles of water? So take 100 grams, yeah, divided by 18.02, get your moles of water. Somebody do that for me? I'm doing this first problem for you, basically, if you're keeping up. So, say that again. So 100 grams of water converted to moles. 5.55 moles of water. Labeling it water so you remember later on that that's moles of water. So then what's this total down here, Levi? 5.55 plus that. 715 moles total. And what is that as a decimal? I do not know, but mole fraction is not multiplied by 100. It's just a decimal, and it's unitless as well. What is that? Okay, well, you guys can figure that part out. Okay, so that's molarity, mass percent, mole fraction, molality. How do I get molality?
Moles over kilograms.
Moles of ethanol over kilograms of kilograms of solvent, which is what in this case?
Water.
Water. What's my kilograms of solvent? 0.1 because it's 100 grams, 0.1 kilograms. Divide, you get your molality. Woo! All right, so I feel okay. You guys are doing examples 1 through 7 exercises on the SMI. And whatever you did not finish on the lab, there's just a couple of conclusion questions. Do not do anything with the lime soda or the lime sports drink because we didn't have that still. Good luck, ACTers tomorrow. And then Savannah, Arushi, and Avery, come send me your request. Bye.